Okay, good afternoon and welcome everyone for this presentation of the 2014 EMS Awards. So you will have here the list of the awards which are presented by the EMS each year. You will see that there is for this year a new one in the Media Awards, and it's likely that there will be other awards for next year, but this will be announced in due time. So I will start with the Young Scientist Award. This one is mainly prepared by, we have an award committee, and you see here the list of the members of the award committee. And they have now, I would say, listed all those travel awards for young scientists. And so I will call them one by one to give them the travel award. So the first of them, Ivo van Hooijdonk. Is that okay? It's right. Okay, it's clearly he has about a paper for shear capacity as predictor of nocturnal boundary layer regimes. And well, you will be giving a presentation that's on Thursday, I think 2:30 in the afternoon, right? In room Virgo. So if you are interested, I invite you to attend this session. Second Young Scientist Travel Award is delivered to Anakis for a paper projecting changes of percentile-based precipitation indices for the 21st century in Central Eastern Europe. She comes from the Edward Lorenz University in Budapest. You will give a presentation on Friday, 11:30, in session UC2. That's in this room, in fact. The third Young Scientist Travel Award is awarded to Rogeros Tapakis from Cyprus University of Technology for a paper on computation of cloud motions for solar irradiance prediction. If you are interested in his presentation, unfortunately it was yesterday. You have no other one during the week? Sorry? You have no other presentation during the week. So, too bad, but maybe some of you already attended it. And the fourth Young Scientist Travel Award is awarded to João Teixeira from the University of Aveiro in Portugal. Paper in nothing coupling mode of particulate matter and measurable field through singular vector decomposition. Same situation you have given your talk yesterday afternoon, right? Now, just a short information about the Outstanding Poster Award. This is something which has been established in 2009. But of course, as the poster, it needs some time, I would say, to analyze all of them, and not all of them are already available. Therefore, it is announced only at the end of the session. So for this year, it will be announced on Friday. But I'm happy at least to remind of the one which was announced last year. And so the 2013 Outstanding Poster Award was awarded to Owen, Knippets and Trechak from the School of Earth and Environment in the University of Leeds in the United Kingdom. And it was Severe European Cyclones, a Storm-Prone Situation Perspective. You probably have already seen it anyway, because it is in the foyer, but it is also on the inner page of the back cover of the program book. So you can see it again immediately if you want. So this one, for this one we have a committee which is looking at all the posters. So here are the names of those who have accepted to go through all the posters and award the Best Poster Award for this year. And as I mentioned already, it will be announced this Friday at 13:15, so in the foyer. So we welcome you to come here for the announcement of the 2014 Poster Award. Coming now to the Young Scientist Award. Now this is a clearly singular award. It is presented annually to acknowledge excellence in young scientists, and it is based on high quality publication. And this year, the Young Scientist Award is awarded to Catherine Birch from the Met Office. Yes, please join me. So her scientific work brings together models and observations to quantify the processes leading to major biases in weather and climate model in both the Arctic and the tropics. And the result of her work are one of the key inputs for further improvement of weather and climate model. And you will be given a Young Scientist Award lecture. And this one will be given on Thursday at 2 o'clock in the room Towers. So I also clearly invite you to attend Catherine's lecture. Now we are moving into the media awards. Clearly, presentations, in fact, of the work which deserves those awards have been presented during the media session this morning. So I hope a lot of you have looked at those presentations, because I must say they were quite impressive. The first one is the EMS TV Weather Forecast Award. And this one is awarded to Tran Thao Lin from the Vietnamese television. And it is about the TV forecast on Super Typhoon I1. And I have to say that the film which we were presented this morning was quite impressive, and was a fantastic mixture of very impressive pictures of the typhoon, which you can probably easily imagine, together also with comparison, allowing to compare the strength of this typhoon to other quite famous typhoon, like Sandy, for example, and also some very practical advices to the public on what they should do, like fix their roof, fix their windows, etc. So it was really a fantastic mix, and we really, I think, the very well deserved prize. You come from very far to receive this prize, and we are quite happy to have you coming here to Europe. That's why we have preferred to have your flag here showing, and it's very nice for you to come and join us today. Now I come to the EMS Outreach and Communication Award. There were several extremely good proposals for this award, and therefore the committee in the end decided that for this year they would give the award to 2 projects. I understand only one of the 2 is here this moment, so at least we will deliver that one. It will, I think, representing the team is Felicity Liggins. So the project is the Met Office STEM Outreach Program. And again, we had an extremely lively presentation from you this morning, showing how you engage with a very large team, in fact, more than 100 participants from the Met Office in explaining and showing and engaging with young people in the UK, and that's something which I hope many will try to follow, and it was also, as I said, quite lively, but quite impressive work, I have to say. So, the award itself. Very well done. The second one, I understand that they are not here, but I will. I hope several of you also have seen the presentation this morning. So it's for the project Turbulence, which is in fact a program on the Czech television, and of a series of many shows, 15 minutes ones, explaining various elements concerning particular climate change, but also other areas which needs more time to be explained to everybody. We were told that unfortunately this now series has stopped, but there is some hope that it could restart, probably in a different way. But it was obviously a very good one, and which was quite successful. And as I said, I hope you had the opportunity to see the presentation this morning on this one. And the last of the media awards, I think the awardee also could not come to Prague. It's a new award which was mainly tested this year, award for achievement in journalism, and the idea is to support and highlight authors who produce outstanding examples of journalism in the field of meteorology and climatology, to bridge the communication gap between science, including its application, and the public. And it was awarded to John Sweeney, Ireland. We didn't have the opportunity to see the outcome, but we're told that it is a fantastic mix also of, I would say, good information, good explanation, and whilst remaining at the perfect right scientific level. I would like now to hand over for a few minutes to the Harry Houghton Foundation. I would like to announce an award which will be delivered by this foundation next year. Dennis, you want to come up?
Okay, thank you, Dominic. Yeah, good afternoon. I think meteorology is fun, and meteorology is also passion for most of you who are here. And with an innovative idea in meteorology, it is also possible to help society. Harry Houghton, he was truly a pioneer of commercial weather services, and he earned his money with meteorology. So he was able to put €500,000 into a foundation, the Harry Houghton Foundation, to encourage other people to have innovative ideas. This foundation awards the Harry Houghton Prize every second year for the best innovative idea in meteorology, which helps to bring society forward. The winner receives €25,000, and everybody is able to participate. Whether you're a professor at a university, a forecaster at the National Met Service, a researcher, or a student. Last year, the prize was awarded to Karolina Stanislavska for her idea, Social Media for Meteorological Prediction and Information. You can find out more about her idea and also the ideas of the other finalists from last year on our website. Innovation for us means new ideas. So only ideas that have not been developed by the proposers or by others. It's not an award for past achievements, but it's an award for ideas for the future. Ideas could be anything, could be new methods or devices that are part of larger applications, but they must be clearly identified and described. The ideas should be sufficiently different from other similar applications so that the jury can understand what is innovative about the idea. Of course, it's also clear that you will retain all the ownership in your idea and it will be kept strictly confidential. So how can you participate and maybe win €25,000? Well, first of all, you should get some information from our website, harryhoughtonprize.org. Then think about fresh new ideas, be a bit creative. You can also brainstorm with others, so groups up to 3 people can apply together. Think out of the box and maybe also dream a bit what you would want to have realized. And then also, please research your idea on the web to verify that it's really new. So what's the process then when you have your idea? Please put together the proposal, which should not be more than 3 pages. So it's really quite lean to participate. Together with some other information required, upload it on our website, harryhoughtonprize.org, until the 10th of March 2015 at the latest. So this is really the deadline. All applications need to be received until then. Then, through a 2-stage process, the jury will select 3 finalists who will be asked to present their idea at the next EMS meeting in September 2015 in Sofia, Bulgaria. The jury will decide at that meeting who will win the prize, and Harry Houghton will present the prize to the winner during the award ceremony in Sofia. So I hope that this has been enough information to make you a bit curious about the prize. Please visit the website, and if you forget the website address, it's also in the program book on page 12. We also have some flyers in the lobby. So the jury is looking forward really to review as many applications as possible from you, and we would be very delighted to have one of you as the prize winner next year. Thank you.
Thank you, Dennis. Now we'll move on to the last but not least, the highest award delivered by the European Med Society. It's called the Silver Medal, and it's delivered annually for persons who have really contributed a lot to the development of meteorology in Europe. And for this year, it has been delivered to Professor Peter Lynch. And I will first ask David Burridge to come and I would say present this year's recipients. I know you know him well, so please, Dave, come up and do your job. It should work.
Good afternoon, everyone. Can you hear me? No. I'm very pleased it's the 5th medal. This is the last one that I ordered a few years ago. Peter Lynch joined the Irish Met Service in 1971. But before that, he launched his professional career in grand style. A double first-class honours in mathematics and mathematical physics from the National University of Ireland, followed swiftly by a master's degree. Then he took up a job, something worthwhile, and his first job was as an operational weather forecaster in the Irish Met Service. This proved to be invaluable later in the application of his research results. During the time he was doing work, he also completed a PhD, probably burning the midnight oil, under the supervision of Ray Bates, another Irish luminary, and his subject was dynamical meteorology. And many of you know about his work in dynamical meteorology, and I'll say a bit about that later. Dynamical meteorology and numerical weather prediction, climate science was his love and his forte, and this is where he stayed for the rest of his long career. During his time at Met Éireann, he served as head of research and training. He was a deputy director, led the HELAM project for 3 years, involving about 100 scientists at the time, and established the Irish National Facility for NWP. He was a PI for FASTEX. The operation was directed from Shannon, and in this role in FASTEX, he contributed much to the success of the field program. And FASTEX set the standard for the ocean-based field campaigns that followed, including those undertaken by Thorpex in the last few years. His published work is vast and of the highest quality. The breadth of topics he's covered is amazing, and any scientist would give their eye teeth for such a record as Peter's. I shall use his work on digital filtering, labeled DFI, to illustrate the widespread applicability of his work. In the early days of numerical weather prediction, getting a forecast model based on the so-called primitive equations to start smoothly and realistically was both difficult but crucial to the success of the resulting forecasts. Then the source of difficulty arose because of the imbalance between the starting values of the model, the starting values for the pressure field or the mass field as the aficionados refer to it, and the wind field. And this failure to cope led to noisy forecasts which were totally unrealistic and was the reason why L.F. Richardson had his grand failure. The science behind the development of schemes to resolve this problem is one of the cornerstones of numerical weather prediction. In the early 70s, the approach was to analyze the mass field or the geopotential field from observations, then derive the wind from a very complex nonlinear differential equation. No wind observations are used. No wind observations were used. So we just measured pressures and heights and solved an equation to get the rest. And even keeping the equation in the right form, keeping it elliptic, as the mathematicians would say, was a problem on some days, and the thing fell apart on the computer. This sledgehammer method could only be used in mid-latitudes. There was no application of this in the tropics. And as the community was gearing up to the first GARP global experiment, this was not acceptable. This was not an acceptable way to do NWP. The community wanted to use the new wind observations and new satellite data. And this led to the development of nonlinear normal mode initialization. That's a mouthful. And this was pioneered by Bernard McIntyre and was used at ECMWF, for example, in its first global models and in the first Figure analyses. This approach served us well for global models, but it was far from perfect and impossible to really use well in other models, limited area models, for example. Peter came up with the general idea of filtering based on the methods of signal processing, and his digital filtering initialization scheme was born. Its generality has led to it being used in global, regional, and non-hydrostatic models, which has to cope with sound waves as well as gravity waves, and variational analysis schemes. I haven't much time for the rest of his research, but another area of fundamental research in which Professor Lynch has made notable contributions is the study of nonlinear low-order Hamiltonian systems. I shall keep DFI in my focus here. DFI provides a nice introduction to Peter's book, The Emergence of NWP, Richardson's Dream. This is an outstanding contribution to the increase in the public understanding of numerical weather prediction, and also it's a joy to read. In this book, Peter brilliantly recreates a setting of early 20th century weather science running through such luminaries as Bjerknes and Margulies, before ending up with Richardson, which must be one of his heroes, and he's certainly one of mine. His DFI resolves Richardson's problem, and Peter completes a successful forecast for Richardson's initial conditions. In a similar vein, he reproduced the first ENIAC forecast on a mobile phone, illustrating not only the playfulness and inquisitiveness of his work, but also the developments in computing since those early days. In 2004, Peter left Met Éireann to take a professorship at the University College Dublin, Ireland, and had Ireland's first university chair for meteorology. He had a major role in establishing the new Irish Meteorology and Climate Centre and developed a very successful academic undergraduate, master's and PhD program. He also established the Climate Change Community Consortium for Ireland, C4I, and the Unified Climate and Synoptic Observing Network Project Tucson. The C4I uses Ireland's first regional climate model based on the Helam prediction system. Peter has also made significant contributions to the European meteorological community. He worked in Helam and led it for 3 years, served on YAMAP and the TELUS board, and was a member of the ECMWF Scientific Advisory Committee for 8 years, and chaired it for the last 2 of these. I was the director of ECMWF at this time, and I was deeply impressed with his fierce intensity, brilliant chairmanship, and afterwards there were drinks and delightful, mischievous talk and gossip. Throughout his distinguished career, Professor Lynch has been an inspiring, visionary, motivator, and skilled leader. He is an excellent teacher and communicator of complex scientific and mathematical topics, and continues to collaborate with others in the publication of scientific papers. In 2012, this was recognized by the Irish community when he was made a Fellow of the Royal Irish Academy. Professor Lynch's lifelong research work, his contributions to operational weather prediction, and his contribution to the European community are exemplary. His pioneering research in the area of NWP and his outreach activities in increasing and enhancing public understanding of meteorology and climatology in Ireland are outstanding. His early experience as a bench forecaster influenced his scientific work enormously and enabled him to make a strong, effective communications between research results and operational applications. For me, the hallmark of the best scientists. Peter, we salute you as a worthy recipient of the EMS Silver Medal. Thank you very much.
Oh, hello.
You can sit only.
No, I don't want to turn. Can you get it here?
I can't do that. I don't know how to do it really.
No,
It's there.
I want it here so I can see people.
I don't see it.
No.
That's not very good. Yes, we have a small technical problem because the image of the presentation would not show up on the screen, which of course doesn't help for the presentation itself.
Well, I'll begin, and then they can fix it, perhaps.
Mm-hmm. Yes. That's what I had in mind, but
No, it's up
no.
above. Thank you. Thank you. Thank you. Apologies for that slight delay. I hope things will go smoother from now on. So, it's a great pleasure to be here in Prague. It's a wonderful city. It's my 4th time being here, and it seems to get better every time. And I'm sure you already found out what a marvelous city it is. Dave counted 5 medals. 3, 4, 5. Maybe I should move on. So anyhow, I'm really very, very honored to be in this. It's really an illustrious list. I feel rather a bit of a blow-in. I don't know how I managed to wangle my way onto the bottom of the list, but there we are. They're really great people. And of course, in 2010, there was an outstanding laureate for this medal. So, my talk, the outline is here. I'll be as brief as I can. I don't see any timer, so should I know the time? Can somebody? Okay. I'll in about 2 hours, I'll stop. So, okay, one of my great heroes is Galileo. You could sort of go overboard and say he invented science. Certainly, he did many wonderful things. Most importantly, perhaps for us, he invented the thermometer, and his student, Evangelista Torricelli, invented the barometer. And that really was the beginning of quantitative meteorology. We were at last able to measure the atmosphere and start from then on to do scientific things about it. Now, there are always spoil sports around. Some people say that Galileo did not drop stuff off the Leaning Tower. I mean, he was there. He wanted to do an experiment. He was in Pisa, and the tower was there. What would you do? Get up there and drop it. And of course, this is supported actually in a recent biography by Heilbronn, and we have it on the authority of Viviani, Galileo's biographer, that he did this experiment. To the dismay of the philosophers, different weights fell at the same speed, confounding Aristotle and amazing the assembled masses. So I certainly believe he went up that tower. He also wrote generally about the universe, and most specifically said the universe is written in the language of mathematics, without which it's impossible to understand a single word of it. People are scared these days to say stuff like that. I think it's great. You know, they can't understand a single word. So I'm going to give you a crash course in mathematics. It's as easy as ABC, though, don't worry. We have an equation like this, A plus B plus C equals 0. It's too hard for us, but maybe one of the terms is small. So if A is small, we can say, well, we have a simpler equation, B plus C equals 0, approximately. That's cool. And that's about the heaviest mathematics that you really need to understand what I'm saying. I'll throw a bit of harder stuff in just to annoy you, but that's the basic idea. So we move on to balance. One of the amazing things about the atmosphere is the persistence of the motion systems. I mean, if you have a balloon that's blown up and you stick a pin in it, there's a bang, and then everything is gone instantly. Whereas in the atmosphere, things just swirl around interminably. You know, why doesn't the air rush in to fill up the low pressure in a hurry? And of course, the crucial factor is we're on a rotating planet, and that rotation dominates the dynamics and influences it very strongly. You take a typical weather map. There's nothing special about this when you see a jet stream across the northern part and a cut-off low to the south. And don't worry about the details, but if you look at the chart 24 hours later, there's not a whole lot of difference. You know, the systems are still there, still more or less in the same place. So the time scales are quite long. And Jules Charney put it in a very nice way. Basically said, if you throw a stone into a resting ocean, the energy is radiated away by gravity waves rather quickly, and soon the ocean is back in a state of quietude. But if the infinite ocean is rotating, then some of the energy is converted into rotational motions, and they persist. So the rotation is strongly causative of persistent motion systems. They're not only on Earth, of course. This is the great red spot on Jupiter, which has been around for some hundreds of years. And in much more recent times, a vortex was discovered at the North Pole of Saturn, and it's still swirling around as far as I know. It'd be good to be a forecaster up there. You just say, swirling tomorrow, swirling the next day. But there's a hexagonal pattern there, which is sort of reminiscent of a Rossby wave. But anyway, the idea is much broader than the Earth. Now, I want to talk a little about the 20th century reanalysis. And in the box there, the text, you can just about read it from here on. So a reanalysis of the troposphere has been done, assimilating only surface observations of synoptic pressure. They're the only atmospheric observations that are used, as well as mean sea surface temperature and sea ice. And what comes out? Well, there's some details. Global reanalysis. I emphasize only surface pressure is used, and there are some technical details. But here on the top panel is the output. So it's a zonally averaged zonal wind component based from plotted from one pole to the other and throughout the troposphere. And you see in both hemispheres, you see a very clearly defined jet core. And below that is the output from the ERA 40 analysis, which of course has used a huge amount of radiosonde satellite data from right throughout the depth of the troposphere. And there's an amazing similarity between them. So how is that we can actually find out about the jet stream from the surface analysis? And of course, the real key is that the atmosphere is in a state of balance, and information about one field gives you a lot of information about others. So the different dynamical fields are strongly coupled. So we get this linkage. I've just learned recently that ERA CLIM 2 is about to appear fairly soon, and that's a similar reanalysis through the 20th century. So obviously before about 1945 or so, there wouldn't have been very much, if any, upper air data. So they're facing the same problem. So it'd be interesting to see that and compare it with what we already have. Okay, so balance is what I'll talk about now, and I'll start with hydrostatic balance. The atmosphere is surprisingly thin. It's only about, the troposphere is only about 10 kilometers deep, yet the radius of the Earth is 6,000, 7,000 kilometers. So it's a very thin layer. You might again ask, like a child would ask, but why is it not even thinner? Why doesn't the air all fall down? Of course, there's something keeping it up there. A parcel of air is being pushed from below by the air beneath it. It's pushed downwards by the air on top of it. And the upward push is slightly greater than the downward push, but that then is balanced more or less exactly by the attraction of gravity. So you get hydrostatic balance. If you look at the vertical equation of motion, you think of it as ABC, with the B and C being the green terms. Two of the terms are much larger than the rest. So if we throw the rest away, we just have the vertical gradient of pressure balancing the attraction due to gravity. And this is the idea of hydrostatic balance. You might say, in a sense, the atmosphere is addicted to hydrostatic balance. If anyone dares to disturb it, it gets very agitated and needs a quick fix. It comes back to hydrostatic balance very rapidly. That's number one kind of balance, but more interesting still is geostrophic balance. And Napier Shaw, one time director of the Met Office, coined the term. It's wonderful what a classical education can do, you know, geostrophy, the earth turning. I mean, today we would invent some appalling acronym for this wind, or call it the Google wind or something dreadful. But geostrophic, we're lucky to have a lovely word like that. And Shaw, I'll come back to shortly. So the idea, of course, is the pressure and wind fields are in balance. And we do see here, if you look at the cutoff low, the air is not blowing into the low, it's blowing around it. And the first one to kind of formulate a rule of thumb for this was Christophorus Buys-Ballot, a Dutch polymath, who noticed by looking at the meager observations available to him, he was able to formulate a rule of thumb. And that's the rule of thumb. In the northern hemisphere, if you stand with your back to the wind, the low pressure is on your left. And actually that contains a profound truth. Of course, it's just a broad rule, an empirical rule, but it nevertheless is quite profound. Some clever guy had a variation on that, which I like to call the GPS version. If you stand with your back to the wind and the low pressure is on your left, you must be in the northern hemisphere. I'm not sure who's responsible for that. I strongly suspect that Raymond Hyde might be behind that formulation. But that's a rule of thumb. What about being more quantitative? Well, the American meteorologist William Ferrell had a much firmer grasp of the dynamical explanation for what was going on here, because he actually wrote down the full equations of motion, including the effects of rotation. I don't know much of the detail of the history, but strangely, he published an essay on the winds in the Nashville Journal of Medicine and Surgery. Maybe it had a higher impact factor. I don't know. Now, it's a little long-winded here. I'm not going to read this, but in essence, Ferrell realized that the rotation of the Earth was a dominant factor, and that it was a centrifugal effect. Moreover, if the air was moving, there was an additional disturbing force. Down at the bottom, he talks about a disturbing force which materially influences the motion. And that was the first really detailed dynamical insight into what's going on. So we have these figures like we see in all the textbooks. If you just look at the left-hand side, there's a pressure gradient force drawing the air in towards the center of the low, but it's counteracted by an outward Coriolis force perpendicular to the motion to the right, and you get a balance and the wind ends up blowing around. If you like more bells and whistles, you can add the centrifugal component and you get something called gradient balance. Okay, so here's the horizontal equation of motion, and we might ask ourselves, is there any steady motion where the time derivative can be dropped? Well, let's drop the time. We're still in trouble because there are three terms here, and it's difficult to know what's going on. We have the advection term, which I'm just for simplicity, I'm calling the centrifugal force, but it's the advection, and the Coriolis term and the pressure gradient term. But I'm saying this is easy as ABC, because we have an equation now with three terms. What if one of them is small? The three together give us what's known as gradient balance, and it's a good approximation to many, many atmospheric motions. But things get simpler if we can throw away one of the terms. If the first one is small, we straight away get geostrophic balance, a balance between the effect, the Coriolis effect of rotation, and the pressure gradient force. Okay, if the middle term is negligible, we get cyclostrophic force, And if the third one is negligible, we get inertial balance. I won't have time to talk of them all, but I'll talk about geostrophic balance. So we have the two terms here, and without worrying about details, we can actually use this to get an expression for the wind. So the wind now, the geostrophic wind, is given in terms of the pressure. And we're used to this, and familiarity tends to breed contempt, but it's an amazing thing, really, that knowing the pressure, we can get the wind. It's very unusual. We can do this. It's strange. And of course, it's behind that ability to analyze the troposphere using only pressures, because we actually implicitly have enormous information about the wind field, although we didn't use any wind observations. So what does this mean for persistence? Well, if we think of a non-rotating Earth and just write the rate of change in terms of the pressure gradient and put in typical values for the system, we get a time scale of a few hours. But we know that storms and so on last more than that. So let's see what happens when the Earth is rotating. Well, if we assume geostrophic balance, just for simplicity, assume the pressure gradient and Coriolis terms cancel, then the advection determines the time scale. And again, putting in typical values, we get a time scale which is an order of magnitude greater. So basically, geostrophic balance implies a much longer time scale. So systems last much longer. Thank goodness. Imagine the horrible task of a forecaster if he had to forecast the gravity waves in full detail. Couldn't be done. So I'm not going to talk the whole way down through the list. It's far too long, but I'll just mention another simplification. The geostrophic wind has the property that under some reasonable assumptions, it's non-divergent. You calculate the divergence, assuming that we can ignore variations in F and rho, then you get a non-divergent flow, which makes things simpler still. Okay, I'm going to look at atmospheric systems of different scales and see how this balance applies. To do that, it's useful to introduce the Rossby number. And the Rossby number is basically the ratio of two terms in that three-way balance. We can think of it as the centrifugal force over the Coriolis force, or the advection term over the Coriolis force. We can also think of it usefully as the spin of the flow divided by the spin of the Earth. It's another way to express it, and this can be useful too. And rather than talk about it, let's look at a map. So this is a fairly standard 500 millibar geopotential and wind field taken from the nice textbook of Marshall and Plum. And since we have the heights and the winds, we should be able to calculate the Rossby number. And sure enough, here's a map of the Rossby number. And the most important thing is that in most of the chart, it's quite small. All around the area that I'm pointing at, it's about 0.1 or 0.2. There's a few hot spots in places, but generally speaking, we can see that it's quite small. So with that in mind, let's look at some atmospheric systems. So we'll start with the largest and then go down in spatial scale to the domestic level. So if you take typical size, typical parameters for an extratropical depression, you find, sure, the Rossby number is small. So geostrophic balance should be good. The wind and the pressure field should be in this harmonious relationship to each other. Gradient balance is a little better, but geostrophic is good. And of course, if we look at a weather map anyone will do, we find the wind behaving itself and blowing around the low in the correct direction. Okay, we'll go downscale now to a tropical cyclone level. Now this is a kind of a double whammy because the wind speed has gone up and the spatial scale has gone down. So typically the Rossby number is now substantially bigger. And it's certainly not small compared to 1. It could be anything from 10 to 100. So geostrophic balance is not going to work here. But gradient balance, which allows for the curvature effect, should be okay. In fact, you might go further and say, you know, if the Rossby number is so small, surely rotation doesn't matter at all. That would be not an unreasonable thing to say. But if you look at the distribution of hurricanes, it's kind of fascinating. This is a chart of the track and intensity of tropical cyclones over quite a long period. And you notice this very marked gap. Near the equator, hurricanes hardly ever happen. There just aren't any. So the Coriolis force, or rather the rotation of the Earth, has to be effective in some way in determining just where these things occur. As often Napier-Shaw has the bon mot, I always find my pen sticks to the paper. I can just hear him saying it. Refuses to move when I try to draw an isobar across the equator. It's a nice way to put it. And anyone who's analyzed tropical charts knows this difficulty. So let's go down scale a little bit more to tornadoes. Now the Rossby number could be anything around, say, 10 to the 4. So clearly geostrophic balance is out the window. Coriolis effect might influence the background flow. It will, in fact, but it's not going to be dominant in the actual internal balance of the system. It's something like 40 years now since a paper appeared in Nature looking at the increase in the occurrence of tornadoes and the way it was correlated with the increase in traffic on the highways. I don't know where this research went later on, but basically because they drive on the right in America, as here, the traffic is generating positive vorticity. And I think there were serious suggestions that maybe we should all drive on the other side. I thought actually it'd be better to start off in New York, stay on the right, and then switch over when you get to Kansas, and then switch back again when you get to Arizona. But anyway, this didn't happen yet. But would it have actually been effective? Well, I don't know, because something like 98% of tornadoes are cyclonic, but just for fun, I had a look at one of the fountains of knowledge, Wikipedia. I looked for anticyclonic tornado, and to my amazement, there are many of them. They actually list many notable anticyclonic tornadoes. So they do occur, and they're not negligible. So maybe if the Americans all drove on the other side of the road, it would just make more of these. I don't think that would help anyone. Okay, to go to the final small scale, of course, we all know about the issue of the plug hole. And the Rossby number there, it could be anything from 100,000 to 1 million. So clearly, we're not going to get any effective rotation. There is somebody who thinks rotation is important, but I don't. Okay. So there, just to summarize, when you have a balance of forces, you can have a steady flow which persists for a long time. So that really is the key to the persistence of the atmospheric motion, is the fact that large terms come very close to cancelling each other. So what's the cause of all this? Of course, it's the rotation, but we need to look in a little more detail. So I'll talk for a few minutes about the Coriolis force, or the Coriolis effect, rather. Newtonian Mechanics talks about an absolute reference system. And Newton's laws are true in any inertial frame. That's a frame that's not accelerating. Of course, on the Earth, we're spinning around. Here in Prague, we're going around at something close to 1,000 kilometers an hour, just due to the rotation of the Earth. So now Newton's laws keep the same form as long as your frame is not accelerating, but they're not covariant under accelerating frames. So we write the law of motion something like this. The change of momentum equals the applied force. We can break it up into components in a nice Cartesian system. That's very nice, but this works only for the Cartesian system. If we take a simple XY frame, they're the equations of motion. But if we just do something innocent like changing to polar coordinates, we get these equations where the green terms have suddenly popped out. So the equations are not covariant. That's to say, they don't keep the same mathematical form when you go to a curvilinear system. With rotation, things get more complex. And I look at a rotating frame. We're standing on the Earth, but the Earth is rotating. So we have a velocity in the absolute sense, and it's given by this vector product, omega being the spin of the Earth, and x is just indicates the position where we're standing. And this is the vector product, And I think this is the root of the difficulty that people have. People have great difficulty getting a kind of conceptual grasp on the Coriolis force. And its vector products are just puzzling. If you ask somebody to explain one to you, they'll start doing this, waving their hands around and talking about corkscrews and so on, and making you more confused than you started. So of course, if you're moving on the Earth, then two things are happening. You have a velocity due to your movement relative to the Earth, coupled with the velocity due to the Earth itself moving. So the absolute velocity has two components. Okay, I want to introduce a mathematical theorem, and I found out relatively recently that the first person to write this down was actually an Irish-born mathematician, Matthew O'Brien, who worked in Cambridge around about 1850. And we think of A as a vector in an inertial frame, and A prime, the same vector, in a rotating frame. Then they're related by this equation. So the absolute change of A is the relative change of A plus the effect of the rotation of the frame. And this I would like to call O'Brien's equation. The physical understanding was already there, but he was the first one to write it down as a vector equation. Vectors were just emerging at that time. His work was actually completely ignored. It was only later when Josiah Willard Gibbs published his work that people started to pay attention. At all events, if we apply this equation to the position vector x, we get what I already had, that the velocity in absolute sense is the sum of the two parts. If we now get cute and apply it again to the velocity, we get an expression for the acceleration. So the absolute acceleration is equal to the relative acceleration plus 3 more bits. I'm not going to go into detail, but the first one is the Coriolis acceleration, second is the centrifugal, and the third one I'm going to forget about. Okay, if we pop these then on the other side of the equation, why would we do that? Well, we want the left-hand side to look like Newton's law. So if we just leave that term on the left, then the new terms begin to look like forces. And that's why we talk about apparent forces. So the Coriolis effect becomes an apparent force. Okay, we can actually do another trick. We can define a new kind of derivative called the intrinsic derivative. And then if we do that, we can actually write Newton's laws in a covariant form so that these are valid in all frames, all rotating frames. But there's a more systematic way to proceed. You can work in terms of energy and take a parcel of air and ask what's the potential energy, what's the kinetic energy, and then form the Lagrangian, and then Lagrange's equations are written here, and they are automatically covariant. And if that's not sufficiently exotic, you can move on to general relativity and ask, like Einstein does, well, why aren't things the same in all frames, all admissible frames? The laws of physics should be the same. Can we use the principle of relativity to deal with the Coriolis force, a Coriolis effect? And in fact, we can, although I have to confess it's not quite as easy as ABC. But there's a wonderful paper has come out just a few months ago in the Quarterly Journal by Martin Charron et al. In Canada, in which they give a full general formulation of the equations of motion in a tensorial form. Now, the point about a tensor equation is it's valid in all frames. It has this property of covariance automatically, so there are good advantages. I'll go pretty fast now. We use kind of ideas that originated with Gauss and Riemann. We can write down a metric, and of course their idea was everything is determined by this metric. So all the geometry and so on. And we can proceed to see what happens if we go to a rotating system. Then we get a metric with extra terms, particularly this fellow. And then we remember, we can write down the actual metric tensor. And we can remember from our general relativity, there was an equation for a geodesic. And it's all plug and play. It looks messy, but it's plug and play. And we get the equations of motion. And sure enough, here's the Coriolis force, and here's the centrifugal force. So why would we do all this? You know, Tensor equations are covariant, so they preserve the form in all frames. Transformations can be handled in a very systematic way. Approximations can be derived very rigorously, and the conservation properties that are really important, angular momentum and energy and so on, can be preserved automatically. So I think there are powerful ideas here. I'm going to skip a little more of this. It breaks my heart to skip, but there we are. What is Galileo to finish off with? Without this understanding, one is wandering around in a dark labyrinth. I wouldn't have wanted you to be wandering around, so I put in some of that stuff. But let me finish now. Dave mentioned Richardson, so I'll just finish with Richardson's forecast. You all know, during the World War I, he computed the pressure change at a single point. He got a number which was physically completely unrealistic. 145 millibars in 6 hours was his predicted change. Yet his method was sound. You know, how can you have it both ways? Well, what he was doing basically is shown on this figure. He had a noisy signal. So if you look at the purple curve and take the rate of change of it, it's represented by the red line. And of course, the essence of the problem is that for a noisy signal, the instantaneous rate of change gives you no guidance to the long-term behavior. So if Richardson had taken many, many, many small steps, he might have actually got a reasonable forecast. But that was totally beyond practicality. So his forecast was repeated on a computer. What took him 2 years happens now in well under a second. And the value that he got was replicated, 145 hectopascals. But when the data was adjusted delicately, the tendency went down to less than 1 millibar per 6 hours. And this is confirmed by the observations which showed that the barometer was steady. So it just goes to show that balanced initial data is essential. It only remains for me to thank the EMS warmly for having invited me here and for giving me this wonderful medal, and to thank you all for listening.